Okay, great. So I want to introduce our next speaker, Neville Hogan, who's a professor of mechanical engineering and brain and cognitive science at MIT. And his talk today is titled Quantitative Models of Human Performance Facilitate Physical Collaboration with Robots. So you can take it away.
Let me share my screen and let me know if it shows up.
Perfect.
I'm going to make that big. Does this work? Doing okay so far?
Perfect.
All right. What I wanted to talk about was that I think we need to pay a bit more attention to coming up with quantitative models of human performance if we're going to get them to work well with robots. And one main point is probably obvious, but it bears repetition, is that humans exhibit spectacular motor performance, despite the fact that we have extremely inferior hardware. And that video, if it shows up on your screen, is Adam Winrich, a whipmaster, and whatever happened there, I hit the wrong button, excuse me. Beg pardon. And this is, I can't pronounce the young lady's name who does ribbon gymnastics. So the main point is that we have this spectacularly complex body. We can manage spectacularly complex objects, but we have very slow muscles, very low bandwidth, very slow neurons, extremely slow, severely delayed feedback. So the question is, well, how do we do that? And we need to model the way we do it, and also that the way we do it may have limitations. So this video can actually manage complex objects. The way we think that certain like
Real quick, I'm not sure video, you can like turn the sound off of or lower the sound on that video.
I think
your voice is hiding your voice.
So how about if I just turn it off?
Perfect.
Sorry about that. Anyway, the idea is that the way that the system works around its own limitations is by using sort of building block dynamic behaviors, which are oscillations, rhythmic behavior, submovements, controlling trajectories, and mechanical impedance to manage interactive dynamics. And the reason that may help is because each of these dynamic primitives may require minimal central control, but may it reduces the need for continuous intervention, but it may still achieve high performance because each primitive building block is itself a highly dynamic behavior. But being an engineer, I'm convinced that there's no free lunch, and so that means that using these dynamic primitives may also imply some limitations, and that's what I'd like to spend some time on. So one study that we've done recently is on studying human interaction with a kinematic constraint. And the task was very simple, just turn a crank. And subjects turned the crank while they were instructed to turn at different constant speeds. They were given visual feedback of the speeds. They were to go clockwise or counterclockwise. Couldn't see their hand, it was occluded from view, but they're able to see visual feedback of the speed they were moving at. So long story short, the main result was that despite instruction and feedback, their speed fluctuated. It varied systematically with crank angle. And although there was no instruction about this, the normal force varied systematically about 0. So one of the things that we were able to do is say, well, one of the ways that you can manage interaction by taking advantage of mechanical impedance is to have a relatively compliant behavior. So if we knew that compliant behavior, we could figure out an underlying motion command which gives rise to the force exerted on the system. So we took an estimate of the subject's mechanical impedance based on postural studies and used it to back compute this quantity that we're calling the zero force trajectory. Essentially, we subtract off the effect of interactive dynamics based on measurements of force, measurements of actual motion. And what that gives us is the following, and that is this so-called zero force trajectory was roughly an elliptical path. So subjects did not generate a circular path, although they came close. The zero force trajectory was roughly elliptical. The interesting thing about it was that if we looked at the relation between speed and curvature of that zero force trajectory, we found that the zero force trajectory slowed down on the curves and sped up on the straights, very similar to the so-called 1/3 power law that's been widely reported for unconstrained movements. So it seems like this speed curvature relation still is present even in a task such as turning a crank, where the curvature is guaranteed to be constant and there's no incentive to vary speed. So what this implies is that the elliptical path is consistent with an underlying motion composed of two primitive oscillations. That's one of the ways you'll generate an ellipsis, by having two non-collinear sinusoids with a phase relationship between them. And that implies that, okay, that simplifies the production of the behavior, but it also implies this limitation of a relation between speed and curvature. Now, in another study, this is a study with Pauline Maurice and Dagmar Sternad, what we did was we looked at humans interacting with a robot, in this case, a haptic master. Haptic master was generating an elliptical path. Subject's task was to simply go along with it and minimize the interaction force. So we gave the subjects three different speed to curvature relationships. So if the movie shows up, in the top left panel, you're seeing the biological speed curvature relationship. That is where speed slows down on the curves, speeds up on the straight parts. We also gave them a constant speed, which you can see. The blue, if you can see it, is the constant speed, and the red is the biological. We also gave them another one, which was we reversed the speed curvature relation. That is where the robot slowed down on the straights and sped up on the curves. And that was presented to subjects. The robot generated the movement. Subject was to simply minimize the force. And again, to cut a long story short, the humans had extreme difficulty performing the non-biological velocity patterns. The performance was best when the speed curvature relation followed the biological pattern. It was dramatically worse when the speed curvature relation reversed the biological pattern. And in addition, in a study of extensive exposure to the constraint to see if subjects could learn to do better, what we found is that without visual feedback, there was no improvement whatsoever. There was some improvement with visual feedback, but even in that case, the best performance that subjects achieved was no better than what they achieved using when they were exposed to the biological velocity pattern. So my point here is that this speed curvature relation, the so-called 1/3 power law, it's consistent with motion composed of primitive oscillations, but it implies that there's a limitation due to this way of composing motion. Now, I should point out that this is not a constraint. It's not hardwired. The non-biological pattern could be learned, but it seems to me that ignoring this preference would compromise human-robot collaboration. We also looked at interaction with complex dynamic objects, where in this case, this is a task again performed with collaboration with Dagmar Sternad. Motivated by carrying a cup of coffee, the idea was to have an object with internal dynamics modeled, in this case, by physical interaction with a haptic master that was programmed to exhibit the behavior of a cart with a pendulum hanging out of it. And the idea here was that, look, if you have long delays, you've got to rely heavily on predictive control based on some sort of internal model, but complex internal models seem unlikely. So the idea here was that, well, subjects simplify the control by using dynamic primitives, and in this case, the dynamic primitive would be a primitive motion, which is a submovement. Well, there are some alternatives known in engineering, and so alternative hypotheses include control via input shaping, which is an engineering method to guarantee control of residual oscillations after movement. Or you could look at different optimization theories, such as minimizing crackle, minimizing hand jerk, and so forth. The details are in the publications at the bottom of the screen. So this was the task: move the cup from from a start position to a target position, guaranteeing zero residual oscillation at the end. And what you found, summarizing results, is that if you looked at the model fit based on, say, the optimization criteria, they didn't work as well as a model fit based on input shaping. And by far the best was obtained when we used simply a superposition of two submovements. So it looks like submovements give you the best description of the human control strategy. But again, as I want to emphasize, is that if there's a benefit from using submovements, there are also limitations. And one limitation that we've studied extensively is to look at the consequence of the limited parameters of these primitive dynamic elements. So in particular, for example, oscillations are not perceived for periods greater than about 2 to 3 seconds. On the other hand, submovements cannot be issued any sooner than about 100 to 300 milliseconds. It's sort of a refractory period. And also submovements can't be extremely long. So if you think about that, if I then ask you to perform a task which required very slow, smooth movement, it's going to be challenging because you can't properly fit your oscillations to it, and you can't fit the submovements to it without having irregularity. So this particular task was to have subjects it was a very simple task, make smooth rhythmic movements between two visually presented targets without stopping at the ends or anywhere else. And it was to be synchronized with a metronome that slowed down, starting with a period of 1 second, then progressively slowed down to a period of 6 seconds, stayed there for a few cycles, then sped back up again to 1 second. And what you found was that, first of all, the subjects were able to perform the task. They could track the metronome reasonably well. On the left, you're seeing single subject's behavior. On the left bottom, you see the average of all subjects. They did reasonably well. But the key thing that we found is that subjects couldn't avoid stopping. They frequently stopped when they were moving slowly, and the length of those stops increased, the dwell time increased progressively with the increase of cycle time. So we then looked at motion profiles. The motion profiles became visibly more irregular as the movement slowed down. And what you're seeing in the graphs is, on the one hand, we fit half sinusoids to each half cycle of the movement, and that fit became poorer as the movement slowed down. On the other side, we fit sub-movements to the movement profile, and we found that there were more sub-movements required as the movements slowed down. So the sub-movement number increased with cycle time. So that's a limitation that seems to be related to the sub-movement motion primitive, and we also saw a limitation related to the oscillatory primitive. But remember that there's interaction as well, and mechanical impedance determines physical interaction, which you can modulate voluntarily, but it's dominated by musculoskeletal geometry. And if you think about it, the main way that we interact with things is through our hands and our feet. And their mechanical impedance is dominated by wrists and ankles. And the point I want to make is that the wrists and ankles have complex musculoskeletal geometry, and that makes a big difference to their effective impedance. So here's some studies that we did with Steve Charles and others. We measured, using a 3-degree of freedom backdrivable wrist robot, we measured the static, stiffness, and dynamics, I'll show you in a minute, of the wrist as a function of displacement in different directions. And the graphs you're seeing in the center are for flexion and extension in the horizontal direction and radial and ulnar deviation in the vertical direction. The first thing I want to point out is that this is a highly nonlinear behavior. The system is much stiffer in radial deviation than ulnar deviation. It's probably not a big surprise. But also there's a pronounced weakness or lack of stiffness in a combination of flexion and ulnar deviation, which is, I believe, being called the dart thrower's movement. So we find that the behavior is highly nonlinear and highly direction dependent, and much more so than we see with, say, hand movement driven by wrist and elbow. Not only that, but if you looked at, and this graph is a little bit hard to understand, but Steve Charles looked at the wrist torque components for different movement durations, and what you're seeing here is these sort of medium gray squares are the torque component related to overcoming stiffness. This sort of horizontal looking line is the torque component due to overcoming gravity. The light gray all the way down here, that's the term due to the damping, which is extremely low in the wrist. And the blackish term at the bottom is the inertia term. And what you can see, oh, and I should mention that the pluses are for outbound and the circles are for inbound. So what you can see is that until you go to very fast movements, these are all 6 subjects, the stiffness and gravity term, but mostly the stiffness term completely dominates for all but the fastest movements. And in fact, in a separate study, we showed that you can completely ignore inertia and you get a very good reproduction of the patterns of movement behavior. We also looked at, in a different study, this is with Young Li, we looked at the ankle mechanical impedance, and it again is highly directional. And what you're seeing here is this is the dorsiflexion, plantarflexion direction in the vertical coordinate and the inversion eversion direction in the horizontal coordinate. The black lines in the middle are with subjects fully relaxed. And notice that this distance here is very small. So you have pronounced weakness or lack of stiffness in inversion. What you're seeing in the red, green, and blue traces are the effect on ankle stiffness of having the tibialis anterior active, the soleus active, and the blue is both together co-activation, all at 10% of maximum voluntary contraction. And what you can see, it's not a surprise, is that as you activate the muscles, the stiffness goes up, especially in the dorsiplantar flexion direction. But on the other hand, there's very little change of the stiffness in the inversion eversion direction. Not only that, but if you extend that out to look at the dynamics of the system, this is the dynamic, essentially the same plot, but for the static, the impedance plotted as a function of frequency. This is the Newton meters per radian, and this is the in the inversion eversion direction, and this is in the flexion extension direction. What you're seeing here on the top row is subject seated. This is bottom row, subjects are standing. What you can again see is that as we increase the magnitude of muscle activation, that the general size of the plot goes up. But notice that the directional characteristic is remarkably invariant to whether you're seated or standing, or whether you're activating muscles or not. And that suggests that it's really of anatomical origin, and you can't, meaning that you can't do much about your inversion weakness. The other thing is that if you look at the effect of muscle activation, what you're seeing here is this is on the left tibialis anterior activity at 10, 15, 20, 25, and 30% of voluntary maximum voluntary contraction. As before, the black curve is relaxed. You can see that the tibialis anterior activity does improve the stiffness in the dorsiplantar flexion direction, but has very little effect in inversion eversion. Soleus activity, very similar. So another important detail is that the ankle muscles are energetically passive, and this is important. So for those of you who are not familiar with it, for passive, that means that the system cannot continuously supply power. Dissipative means it continuously absorbs power. And the reason that's important is that if I have a system that's passive or dissipative, that's sufficient, not necessary, but sufficient to ensure coupled stability in physical interactions. And what these plots here show is that the system is not only passive, but highly dissipative, especially around about the region where you see the transition from stiffness dominated to inertia dominated behavior. So the message I want to leave you with about quantitative models of human performance is that dynamic behavior building blocks can account for human performance. These dynamic primitives, in my view, are fundamental. They provide performance benefits that allow the biological system to offset its substantial limitations, but they come with concomitant limitations, and to ignore them, I think, would compromise human-robot interaction or collaboration. And when you go look at interaction dynamics, as far as I can tell, the major limitations are dominated by musculoskeletal geometry. Now, the biological system may take advantage of that if it needs very low impedance. It may choose these directions, such as the thrower's motion to achieve that. On the other hand, they also mean that if you needed high stiffness in those directions, I don't think you can get it. And that's consistent with my own observation that if you ask people when they sprain their ankles, which way does their foot move, it's in inversion. So you really have no control in that direction. You may take advantage of it, but you can't do much about it. So that let me stop here, acknowledge the many sources of support, and open for questions.
Excellent, thanks. So we have a few questions. First is from Morad asking, is the human impedance at the task level estimated from the human joint mechanical impedance, hence somehow from muscular activities and the musculoskeletal human model?
I'm not sure I got the question. Let me stop sharing so I can pick up the Q&A.
Yeah.
Just a second. So
I think it's getting at the question of how one goes about measuring like human mechanical impedance at the task level. Are you measuring it the joint level? Are you using like using a model? Are you using EMG muscular activity?
So all the measurements that we've been made are based on external perturbation. So for example, the ankle impedance measurements were made by externally perturbing the ankle in 2 degrees of freedom and measuring the corresponding motion. The wrist impedance measurements were made by a 3 degree of freedom by triangle Roma that was able to apply torques in 3 degrees of freedom, measure motions in 3 degrees of freedom. We can then, knowing the kinematics, we can back compute to what the joint level, the joint space impedance is, but that's not the way we make the measurements. So if task level means external, that's what we did.
Okay. The next question is from Jiao Feng asking, what are the differences between motion and interaction primitives? And can you give an example?
Yeah, okay, so motion primitives, for example, are oscillation, just moving around. You can do that in free space. There's no interaction needed. Submovements, for example, a transition from one posture to another with a stereotyped speed profile, no interaction involved. The idea of these dynamic motion primitives has been explored extensively in the robotics literature. I think Aki Eisbert and Stefan Schall, for example, are prominent in this area. That's fine, but that's not the same as interaction. So as soon as I go interact with something, I have to allow for the fact that there's a relation between force and motion. But if I just look at the force and motion all by itself, that's not sufficient to determine all of what's going on. Because, for example, think about stiffness. I have to have 2 inputs for every 1 output. So let's say I describe stiffness as having a force output. Well, I've got to tell you what the motion at the point of contact is, but I also got to tell you the reference point where the force goes to 0. So that's what we call the 0 force trajectory. So to manage interaction, the model we're using, and I can go into the details, but I probably won't at this time, assumes that the motion primitives are encoded in the 0 force trajectory, and the interaction primitive determines the force evoked by deviation of the actual motion from that 0 force motion. I don't know if that was it.
Another question is from Erwin asking, do you have an idea whether these task level impedances are due to nonlinear muscle mechanical impedance or due to reflex loops or something else?
Yeah, that's a great question. Short answer is I don't know. I think the dominant behavior is intrinsic muscle behavior. But I'm not sure that we have good information about that. Clearly, the spinal reflex loops do play a role. The information that's available to us from studies, for example, Steve Scott studies of, he's looked at humans and monkeys, tracing neural activity both from spinal cord up to cortex. Under normal circumstances, Steve has shown that the reflex activity is extremely hard to find. I mean, he's able to find short latency, the M1 and M2 and M3 reflex responses. And during normal movement, Steve is finding that there's just very little going on. So my guess, and it's really only a guess, is that what's going on is that the reflexes are set up to manage the muscle. So as long as the muscle is doing what the central nervous system thinks it should be doing, reflexes don't do much. But as soon as you find a deviation from that, spindles, for example, respond very rapidly to deviation from the contraction of the spindle determined by the gamma motor neuron system. So it's like a local muscle management it's what's being managed by the reflex. But having said that, that's a very hard question to answer. The weakness of the work that we've done, we've applied in the dynamic impedance measurements, we applied stochastic perturbations to measure impedance. A concern is that the stochastic perturbation may saturate the spindles and essentially turn them off. So we're not seeing any spindle-mediated impedance. So really don't know the answer.
Okay. Well, thank you very much.
I have an extra question, if I can ask. Do you think the laws that you find, the observation you find, would hold also if you're interacting with a more complex robot, like a humanoid?
Again, I have no way of answering that. I mean, what we've seen is the work done with Dagmar on that task involving internal dynamics was intended to get at the problem of how do humans manage complexity? And complexity comes in at least two forms. One is kinematic complexity with lots of degrees of freedom, and the other is dynamic complexity with internal dynamics. And it looks like, from what we're seeing so far, it looks like basically humans try to get away with simple strategies. So for example, treating the management of internal dynamics by saying, I'm just going to superimpose some number of sub-movements until I get something acceptable, seems to be what they're doing. I think a similar approach will apply to managing kinematic complexity. And in a completely different line of research, we've been able to show that you can use the actuator level, the joint level impedance, you can use that to manage kinematic complexity, including very high dimensional redundancy. For example, there's no need to solve inverse kinematics, no need to do non-space projections. We get excellent performance just by using the superposition properties of impedance. But that's a different talk.
Okay.
Great. Well, thank you very much. And